Morning, folks. All right, so I have two quick housekeeping announcements before I start. The first is I've done enough of these events and I've seen enough of the pictures from the podium where I've completely sweat through business attire. So I'm owning the fact that I'm a filthy sweat monster and dressing accordingly today. And for those of you who are tweeting, if we can get hashtag Bio-IT15 to trend along with filthy sweat monster, that might not be a bad outcome for a Wednesday morning. So the second bit of housekeeping is probably 95% of my slides are new, and I've got a lot. I won't even tell you how many I have because you'll probably run. So I'm a little bit concerned about the timing, and particularly ending, because I'm one of those speakers who hates to go over time and then inconvenience everybody else for the rest of the day. So I'm probably going to err on the side of going faster than even normal. So just, I guess, be prepared and let's buckle in. All right, so this is normally when I do my origin story, but I'm tired of repeating it. This is how I'm supposed to tell you how I went from science to software to infrastructure, but I'm going to skip it in the interest of time. The more interesting thing is the people that I work with and the people who back me up. So the reason why I'm here, the reason why BioTeam gets invited to these events is that we are a company of scientists who are forced to learn IT in order to get our research done. And so what we found is that there's a really fun and really interesting business niche if you can solve scientific problems that have a hardcore IT component, but more importantly, if you could do it in sort of an independent, objective, and vendor-neutral way. So our little claim to fame in this market niche is we try to be the sort of honest and objective professional services branch in this group. And so honestly, a lot of it, in previous years, the reason why I get invited to events like this is that in any given year, BioTeam is probably in and out of 40 or 50 different environments. And we range from government labs, national labs, military, pharmaceutical, biotechs, big startup, small startup, stealth mode venture-funded firms, nonprofit university. And the really cool thing is that because we bounce around as consultants, we get to see how many different groups of smart people tackle the same problem. And many of our customers allow us to talk in general terms about what we see. So because we're in and out of so many environments, we have kind of a big picture view where we can talk about trends and pain points and horrific mistakes that we've seen that shouldn't be repeated elsewhere. So this is typically the reason why you get someone from a company like BioTeam kind of doing this open-ended talk. The second major change for me is that in previous years, I used to do this talk where I was basically talking exclusively from my own focus. And I would always put a big disclaimer in my talk because most of my world is industrial and commercial. I do pharmaceutical, biotech, nonprofit universities. And I really am trying to say, I'm not an expert, I'm not a pundit, I'm not trying to preach for you. And you need to be relatively cynical about what I say and pass it through your own filters. This is even more important in 2015 because one of the things that we've done is we've staffed up a lot. And we've staffed up in particular with some crazy smart dudes and women who are smarter than me and are working on completely other different projects than I normally work on. And I would say more and more of my talk this year is influenced from the practices and lessons that I've learned from my coworkers. And so I'm trying to blend in a little bit of what I've learned from others. And it's been an interesting journey. I was fairly set in my ways. And now that I'm working with a much bigger infrastructure and HPC team, people who are working on far bigger projects than I normally work on, I'm trying to sort of bring those thoughts and practices into my talk. So that was a little bit insufferable. I want to sort of talk a little bit about trends and steal some bits from last year's slides. So I always start these talks out by the meta position, which is why are we actually here? Why do you come listen to me every year, every couple of years? It is still a really dangerous and scary time to be involved in the business of doing infrastructure or IT to support data-intensive science. The bottom line, the simplest way to articulate it is that bench science and laboratory protocols are changing month to month, and my most aggressively funded biotech companies can afford a major data center refresh every 2 or 3 years. The refresh cycle is much longer and much slower as you expand out to other organizations and institutions. So the problem that we're facing here is, I'm talking over my slides already, is the science is changing far faster than I could build infrastructure and data centers. So our job, and maybe the job of some of you infrastructure or server people in the room here, is that we've got a really scary proposition. We have to build data-intensive scientific computing environments that can survive a life cycle of years in the face of science that changes every week or month to month. So it's a scary time, but it's also a pretty exhilarating time to be doing this type of work. So I've already talked over this. I'll move on. So the other thing, and I'm recycling some content from last year as well, is that 5-10 years ago, let's put it this way, all of the easy problems and all of the easy approaches have been tackled. I used to put servers and disk and storage under wet lab benches, stuck underneath an instrument underneath the lab table, or cases like this, we'd roll a rack into a lab because we really couldn't do anything else. Those days are over. They've been over for close to 10 years at this point. So, this is kind of the new normal for us. This is, 2,000 cores, 2 petabytes, supporting maybe 20 scientists. This is the type of stuff that we deal with every single day. New normal, new normal. new normal. And this picture was actually taken at the Broad Institute a couple of years ago. And speaking of the Broad Institute and really smart former BioTeam people who think a lot about infrastructure, if you really want to hear about Broad, and in particular because they're doing some really, really innovative stuff, Broad is one of the examples that I hold out, like Broad, Sanger, EBI, Beijing Genome Institute. There's a tier of players in our space who operate at a league above and beyond most of us in the room. So the really cool thing is that if you watch EBI, Sanger, Broad, and BGI, what they're doing now is probably what we're going to be doing a couple years down the road. So I always tell people, sort of follow the big folks. And Duan tomorrow should be a really interesting talk. And the other thing is that he's in a track where the preceding speakers are Data Direct and Cumulo. And so there's probably going to be some interesting information there as well. So moving on a little bit into trends, the first one I want to talk about, because it's near and dear to my heart, is the sort of revolution that's happening with infrastructure automation, configuration management, and DevOps. And it's time to be really blunt. This is really the blunt slide. I was a little bit more weasel wordy in other years, but the fact of the matter is, if you're a sysadmin today, it doesn't matter if it's Linux or Windows. If you can't script, your upward mobility is stopped, and you're probably going to have a very hard time getting a job in another company. That is the blunt truth about the way the trends are going these days. It's not just cloud and VMware and virtualization. We're entering an era where basically everything is going to have an API. Our networks, our switches, our firewalls, our switch routers, hell, the doors to the cabinets in the data center are going to have an API. And so the problem is that this stuff used to be relegated to the Netflixes of the world that needed to manage entire fleets of thousands of servers running in Amazon. That was true years ago. It's not true today. All of the magic DevOps, configuration management, and orchestration stuff has been percolating through industry and in our organizations for a very, very long time. So the problem is that I'm really firm in the camp that you need to learn how to do this stuff. And the upside is that you'll be able to do a lot more with a lot less, and you'll probably be able to do it with your laptop from your house, rather than going into the data center and touching buttons and pulling cables and doing things like that. The same advice applies to organizations. An organization used to be able to say, well, we're not really seriously on the cloud yet, so we're not going to look at this crazy DevOps stuff. The fact is that it's already in your organization, or if not, it should be, and it's already sort of being a transformational focus within a company. And the problem is that, and I'll say the word force multiplier. I hate buzzwords, but it is an actual force multiplier. If you are familiar with management saying, staffing constraints, budget constraints, we need to do more with less, one of the actual no BS solutions to doing more with less is sort of embracing infrastructure automation and configuration management stuff. So the problem is that if you're a company organization or an organization and you're not doing this in 2015, it implies certain things about your leadership, your philosophical stance, and your operational practices. And the interesting thing is that your competition may not be or may not share those philosophies. And they're probably getting ready to spank you out in the marketplace if you're not up there. So the warning for DevOps and infrastructure stuff applies both to sysadmins as well as organizations. You need to jump on board now, or the competition is going to blow you out of the water. When it comes to particular stacks, I'm a member of the Ops Code Army. I like Chef. I'm required by law to hate any Puppet user that I encounter. But the fact of the matter is that it really doesn't matter what stack you choose. What you have to do is you have to find a stack that works for you. You have to find a stack that many different groups in your organization are going to buy into. It really stinks when you're using Chef and the global infrastructure people are Puppet people. It's really worth doing the groundwork and getting on the same stack and leveraging it across the enterprise and not just research. So the other thing that is that this advice doesn't just apply to organizations and people. If you're a network engineer, you're going to need more than that Cisco certification to continue in your job and continue on doing really interesting things. The same level of automation is coming. I mean, SDN is a little bit buzzwordy. It's not super useful in a lot of contexts right now, but it's coming and it's going to be huge. So one of the examples here is this is an Internet 2 self-service software-defined networking portal. It allows you to go into a web page and with the right credentials sort of self-create VLANs and circuits over Internet 2. This is one of the more practical uses of software-defined networking that I've seen. It's baked into Internet 2 AL2S service right now, but it's coming to more and more stuff. It's coming to OpenStack. It's coming to private clouds. It's coming to hybrid clouds. So if this type of stuff interests you, I've got another set of homework here. Is later on in the afternoon today, Internet 2 is going to be talking about their stuff, and hopefully, I didn't really see the slides, but they'll probably be showing you some of the interesting things they're doing with OpenFlow and software-defined networking at this point. So homework assignment number 2, if you like this stuff, is out there. So transitioning on to compute. I sort of try to go, compute, network, storage, things like that. So the next topic here is compute. Generally speaking, there's some changes, not a lot of huge changes in 2015. Clusters are still the baseline. Even our laboratory instruments know how to submit jobs to an HPC scheduler. The only mini trend that I've noticed is I come from a long line of open source zealots. I was, Grid Engine, BioPerl, BioJava, all that stuff. There is an interesting trend in 2015 where resource allocation is getting a little bit hairier. It's harder to do, for instance, CPU core binding and memory binding and do deep GPU integration on a job scheduler. And you're starting to see a little bit of a trend with the commercial version of Grid Engine from Univa, who has a booth here today, is slowly starting to take over the open source Grid Engine environment in my world. So that's a little bit of a trend from the industry side. I'm not sure if that applies to other industries and other fields. So the other thing for me is that compute, it still feels to me like a solved problem. It's a commodity. It doesn't really cost much, regardless of who you buy it from. As long as you have the budget, it's not a particularly challenging problem to solve. The only caveat is that I got the opportunity to work for a team that's designing a 60,000 CPU core HPC environment. That is a little bit hard. That is a little bit challenging. So I have to put a little caveat there. So if I'd said compute was boring in 2015, the 60,000 core people would get really upset. So the second thing, and this is sort of a minor trend, is that if you look at what's going on with servers, the new Intel stuff is actually driving 40 gig network cards today. So what that means is, from blunt and sort of painful experience of my own, if your servers and your infrastructure are starting to play at 10 gig and higher speeds, you actually have to care a little bit more about the networking cards in your systems. You have to care a little bit more and possibly do a little bit of kernel and operating system tuning that you probably didn't have to do when you're back in sort of the 1 gigabit land and before. So a little bit of a compute trend is we're having to do a little bit more focus on kernel tuning and TCP network stack tuning. And it's going to become more and more of a problem as we go from 10 gig to 40 gig and faster. So the other thing that's really interesting is that the days of building a scientific computing environment from a monolithic block of the same darn servers have long been over. The clear design pattern in our space is you choose building blocks. You buy and deploy the building blocks that make the most sense for your business case or your scientific use case. This is an example of the building blocks that we routinely see. I won't talk over them at all. But the main take-home point here is you can't just buy 100 nodes and set up an HPC environment. You probably need to make some distinctions between what each node is optimized for. So this is a short list of some of the different node types we've wedged into HPC environments. And transitioning a little bit to a picture, I don't know if anybody recognizes this. This is what it looks like when you pack 96 DIMMs and 1.5 terabytes of RAM into a server. So this is an example of one of our fat or sort of large memory nodes. And it's an interesting picture. It's an interesting form factor, so I wanted to throw it in there. The other interesting packaging stuff is started to be new this year. If you looked at high-density GPUs in previous years, it was either 1 or 2 GPUs per server, or you would do weird things with PCI expansion shelves, and you would have all this separate stuff. You're starting to see the sort of fat GPU building block example. And I stole this picture from nortech.com. We've been deploying fat GPU building blocks. I just didn't have a clear picture of one of the ones that we deployed this year. So the other thing that I always want to touch on is that there's a lot of innovation and a lot of interesting stuff happening with FPGAs and coprocessors and what I sort of call the exotic hardware acceleration space. The downside is that if I want to be blunt about it, they have their use, but it's not going to take over the world. The real reason why is that they just don't work by magic. There's a significant sort of activation energy you need to get over before you can make realistic use of an FPGA or an Intel Phi card. So where you're starting to see them is they're being deployed as point solutions for a particular pain point, particularly environments where you have the human resources who can invest in algorithm development and sort of hardcore scientific software development. And then finally, the other thing where like a Phi coprocessor card makes sense is if you cherry pick the most important analytical workflows and you have a sincere desire to make them an order of magnitude faster, there's definitely room in that world for sort of hardware accelerated stuff. But it's definitely point solution rather than sort of generic and pervasive at this point. And if you like the concept of Phis and coprocessors, one of the really cool new hires from BioTeam, and we stole him from a national lab this year, is Banu. Banu's done a ridiculous amount of work doing really, really hardcore bioinformatics on Phi coprocessor cards. And actually, one of the luncheon presentations today is going to be Banu talking about this as well. So if you're interested in the coprocessor stuff, stick around in this meeting room, and you'll get to see a little bit about sort of what the state of the art is in the industry right now. So this is new. I didn't really put in a converged infrastructure deck into last year's slide. And if you look at the little the call out at the bottom, that is a 100 gig switch router. It's real. We deployed it in a life science environment this year. 100 gig is here. It's a little bit scary to say that. I didn't have 100 gig deployed when I gave this talk last year in 2014. So the converged stuff is really interesting. And this follows in on the workshop that we ran, which was really, really interesting yesterday. The idea here is that it's not yet something that's widespread. I won't even really call it sort of one of the fundamental trends that I call out, but it's something to keep an eye on because most of the time I see the hyperconverged stuff in a new greenfield project or when we're completely tearing down and rebuilding a data center environment. So it feels like the scale-out petabyte, scale-out NAS stuff. This is an area where we probably wait for a little while and we see how the big organizations, the supercomputing sites, the Broads, the BGIs, the Sangers of the world, see what they do in this space, and then we'll probably end up sort of plagiarizing their best practices in the years to come. The small examples here from some projects is that networking is getting more and more interesting in this space, and we've seen at least one project where they completely redesigned their approach to networking within the organization. They're actually deploying what they call an ISP model, everything virtual, everything remotely automated, and the idea being is that they sort of operate as basically as a business service, providing VLANs and connectivity to whether it's an instrument or an end user desktop. The other obvious hyperconverged stuff is what's going on in the virtualization space. You're now seeing VMware servers or virtualization servers that not only are running the hypervisor, but the chassis itself is crammed with disk, CPUs, and network, and you're doing really, really intensive stuff within the same chassis. Avere is front-ending all sorts of stuff, and as of last week, they're now talking to the Google Cloud as well as Amazon. Another really cool example is from DDN. DDN's had this capability for a while. DDN makes big storage arrays. They're sort of the go-to choice if you're doing GPFS or parallel file systems work in the supercomputing world. But DDN has had the ability to run applications on their storage shelves for a while. So you're starting to see now where even getting storage shelves have the ability to run hypervisor and run interesting bits of servers and software stuff. iRods is another example, and I'm going to talk about that a little bit later on, particularly because iRods used in conjunction with an object store is starting to get really, really interesting. So the other example of the convergence in IT is this is something that I've been watching. I don't see a lot of InfiniBand in my world. I do InfiniBand to make computational chemists and modelers happy. I do InfiniBand between a parallel file system nodes or things like that. But there's some really, really interesting stuff going on in the InfiniBand space, particularly with 100 gig EDR, which is sort of on the market and becoming generally available this year. But if you combine that with the Mellanox virtual, I think it's virtual protocol interfaces, you can simultaneously run 100 gig Ethernet, 100 gig InfiniBand. You can run mixed mode. You can run entirely on InfiniBand with IP over IV on top. There's some really interesting stuff you can do if you go into this sort of InfiniBand-based converged infrastructure stuff. In particular, with the dual port card simultaneously running InfiniBand or Ethernet or switching back and forth, really, really lends some sort of transformational capabilities to your infrastructure. And this is one of the areas that we're going to be focusing on in 2015 and beyond. I've already talked over this slide. The idea being is that, in particularly when it comes to InfiniBand, there's a lot of interesting things you can do when your message passing, your storage, and your network traffic is all on sort of one virtualized, automatable, single management, network fabric. The other thing is that if you're looking at this from a large greenfield project, if you compare the cost of doing all InfiniBand and running Ethernet where you need to versus the cost of running 10 gig Ethernet out to everything else, we ran the numbers. You're solidly in the land of $1 million or $2 million worth of CapEx savings at particular scales. So the other thing I should announce here is you've probably seen some signs, I think we mentioned it before, is for the first time ever, BioTeam is going to start a conference series. So we're doing this in September. We're doing it with CHI, the people who organize these meetings. So if you attended the workshop yesterday and you liked it, or this idea of sort of hyperconvergence in IT is an interesting topic for you, we're going to try to get a meeting of the minds together in September of this year. And hopefully it's going to take off from there and grow. Information is there. We've got the full agenda and all the brochure stuff at our booth. That's probably the sort of I hate putting marketing stuff in my talks, but this is important enough. And if we can get the right set of people in the room in San Francisco in September, it's going to be an awesome event. So moving on from convergent infrastructure to cloud stuff, it's still real, it's still useful, it's getting stronger and stronger. Just like big data, it's absolutely polluted by marketing and BS, and you sort of have to be really cynical about what you can and can't do. Not the least of which is you cannot use the word cloud in a mixed audience without agreeing on what you're talking about. The word cloud is utterly polluted. You have to define the word cloud before you have any meaningful expectations about having a good conversation with something. So I'll do a little bit of a recap and then a few slides on some of the firsts for us this year. So I continue to articulate that the primary driver for cloud adoption in the life sciences is not cost or economic based. It's actually capability based. If you talk to the sort of senior leadership of big science organizations, they're looking at a future that is increasingly involving multi-site, multi-party collaboration. In particular, you might be competing and you might be collaborating in one area with a company that might be your frenemy in another area. And so if you're competing with someone that you might also want to collaborate with, you're not going to open your firewall. You're not going to give those people VPN credentials. The cloud is turning out to be a very, very interesting neutral meeting ground for multi-party collaboration. And going on from there, everything from laboratory instruments writing directly to object stores. I continue to argue that it's more of a capability play than it is an economic play, although the economic benefits are real and tangible as long as you're careful about your design and your spend optimization. So a little bit of milestones for us. It's actually been a big year for us on both Google and Amazon. So 2014 was the first time we actually lit up a 10 gig connection to Amazon. It's the first time we actually used Amazon Direct Connect peering at any significant scale. 2014 was also the first time we used Internet 2 as a way of getting direct access to the Amazon cloud or the Google cloud if you wanted to go that way. The other big milestone for us is, if you've seen me talk over the years, I talk a lot about Amazon. Years ago, I would make a very strong argument that the only player from an infrastructure perspective is Amazon. Last year, I said Google was viable. I had a couple of asterisks. It was sort of use case dependent. 2014 was the first year that we actually deployed not only a production-grade application onto the Google Cloud, we actually made direct use of the Google Genomics product stack and the Google Genomics API. So if the Amazon stuff, particularly 10 gigabit, template-driven instant HPC, multiple VPC architecture design, security, and Internet 2, if that sounds interesting, then tomorrow at 10:40, there's Jason from Biogen is going to be talking about this sort of thing, and you will find many of the concepts that I just mentioned covered in detail in his talk. If you happen to be more interested or equally interested on the Google side of things, this is really all I can say. We did a production project with Autism Speaks. It's a variant analysis application. Deep confidentiality agreements. This is literally the only screenshot I'm allowed to show in public. So I can't talk about anything else, but the people who worked on the Google Genomics stuff for BioTeam, they're going to be hanging out at the booth. So if you want to do a little bit of a dive or talk more about Google and Google Cloud, stop by the BioTeam booth, and we've got some nerds who'll be happy to chat with you. So moving on from cloud into storage land, this is where it starts to get a little bit interesting. So a lot of attention to this in 2014. I'd refer you to my old slides because I did a ridiculous amount of slides last year on storage. So I really want to concentrate on just kind of a quick recap and a little bit of new stuff. So it's still a huge and painful problem for me. It's still a tremendous opportunity if my goal is to waste fantastic amounts of money. Petabytes class storage hasn't been scary for a long time. The argument I made last year is even more true. The days of having a monolithic, single vendor, single tier scientific computing storage environment are over. It's clear that we need multiple tiers, and it's probably clear that the tiers are going to be from multiple vendors. You can do it in all-in-one vendor sort of nirvana, but if you're mixing and matching, you've got a little bit more freedom and a little bit more capability if you go that way. So I'm going to throw this up here as just an example of the type of tiers that I see. I would encourage you to ignore the sizes because the sizes depend on your organization, your workflow. But most people probably need a really speedy tier to handle instrument data ingest and any scientific workloads that they have that are performance sensitive. That tends to be a fairly small tier. That's the sort of thin wedge of your scientific storage footprint. The major tier, and it could be 50 terabytes, it could be 2 petabytes, is your sort of active processing tier. This is what your high performance computing environment is doing. This is what your statisticians are using to crunch numbers. This is where the sort of day-to-day science happens, where science hits applications, hits storage. And then finally down at the bottom here, there's a lot of use cases and there's a lot of requirements to store large amounts of data, but the data itself is not particularly valuable because it's open access. You can get it from the internet again. If you lose it or if the storage array blows up, it's more of an inconvenience than a critical business hit. So there's some interesting stuff going on there if you want the trash tier or the data lake tier where you just need a big pile of space to store interesting data, but the data is not particularly sensitive or valuable. And then finally, there are more and more performance-sensitive workloads now in our world, and so there's generally an emerging use case for having the sort of fast scratch or sort of fast active operational tier. So it's not a trend. It's going to take us a couple of years to get here, but I'm definitely in the camp. I've been converted over the last couple of years. The future of scientific data is object-based. Full stop, period. That's what we're going to be doing. It's going to take us a couple of years to get there, but object is the way. I expect to probably talk a lot more about object storage next year. So the other, if you want to sort of check my facts, just go walk the show floor and see how many object store vendors are in the audience. Just off the top of my head, I know Amplidata, Avere, CleverSafe, DDN, Swift are all here. There's also, and I forgot to put a homework slide about this, Fred Hutch Cancer Institute is doing some really interesting things at large scale with Swift. And somewhere on the agenda this week, there's a Fred Hutch object storage talk that you should probably check out. They've also put their talks on YouTube's before. So if you miss the Fred Hutch talk, chances are you can do a little bit of Google, a little bit of internet searching and find it. So a little bit about why I think object storage is the future. The issue here is that if you talk to an object storage salesperson, they're going to talk to you about economics and scalability and the magical benefits of erasure coding across multiple sites. The fact of the matter is that that's really interesting, and I like economics, and I love erasure coding. Object store delivers to me something that's far more valuable than that. And the idea here is I'll show you that, in a standard file and folder world, this is all of the information that I have on the file system, on the disk about a particular piece of scientific data. I know who owns it, I know what group they're on, I know a little bit about read, write, execute, and I kind of have some timestamps if my clocks are correct about who meddled with the file last. This, from a scientific perspective, is crap. We need to store and track far more information about scientific data than the minuscule amount of information that the sort of POSIX file and folder world allows us. So if I just brain dump this, I won't even pretend this is a complete list, but I would encourage you as a thought exercise, think about the scientific data that you care most about, and think about the questions that you would love to have answered about that data, and how they would be permanently associated with that file, indexable, searchable, and easily retrievable. So this is not enough. When it comes to scientific data, this is the type of stuff that I want associated with every single file that I put on disk. And the blunt truth is that there's ways to store this information. They're other than object stores, but object storage right now is the sort of path of least resistance. I'll talk a little bit about the ways people have done this before. If you talk about metadata-aware storage, there's a couple of different, you can go out and talk to the people who have been doing this successfully. There's a lot of people who are doing this in sort of homegrown relational database management systems. There's people who've customized LIMS software and sample tracking software system to do this. The other big player in our space is iRods. iRods. There's an open source version of iRods, but there's also a commercial version from a company called General Atomics, and General Atomics is here on the show floor and speaking about this stuff as well. But so the interesting thing here is that if you look at the people who've done successful metadata-aware storage thing, they've done it, but they've done it at a fairly high cost in technology, human staffing, and operational effort. The only people I've seen successfully using iRods at a very large production scale are people who have dedicated full-time software engineers, one or possibly two, associated with a project. So you have to commit to it if you're going to get it to work. The benefit of object storage is that the operational commitment, what you have to do to sort of add that metadata awareness to your file, is a lot less. You just articulate it at the time you're putting your file into the object store. So my gut feeling is that the economic and tech benefits, particularly erasure coding and scale, you have multi-million-dollar CapEx advantages if you have multi-petabyte replication and you could take advantage of erasure coding. But for me, in the same way that capability is driving cloud adoption, it's the metadata-aware feature of object storage that I think is going to drive us towards sort of very large-scale use of objects in the future. So the upside, though, is that I think it's going to, we move very slow. We have hundreds of legacy applications. We are never going to rewrite many of our scientific pipelines to understand objects when right now they understand files and folders just well. So you've got time. It's going to take years for us to transition. I'd encourage you to go talk to the object people in the audience, check out the Fred Hutch talk and a few other things. It should be on your planning roadmap for the next couple of years. And in particular, I would encourage you, particularly those of you who talk to senior management about this stuff, it's not just the economics and the technology. It's the metadata, the tagging, the searching. And if you're doing an RFI or a large-scale project, you probably want to be scoring your object storage vendors on how well they do metadata, search, query, and retrieve as well. It's not just the financial bits. So on the final side, if you want to combine two good things, BioTeam has done some interesting stuff with CleverSafe, in particular putting iRods on top of an object store. So if that sounds interesting to you, or if it sounds like a nightmare and you just want a little bit more of an explanation, you can come talk to the CleverSafe people or come talk to us at our booth, and we'll sort of show you what we've done there. So hopefully, time-wise, all right, I'm about halfway in. I think I might be doing OK. Hopefully, I haven't stunned you senseless. I'll talk a little bit more about some war stories from 2014. So the interesting thing with storage is that primary storage is still a big challenge for us, but the most interesting projects that I've worked on have actually been the edge cases. And it's been the edge cases at the very low end and the edge cases at the very high end. And I want to give you a couple of sort of real-world stories from this year. So this was a really interesting project, probably one of the more fun projects I did in 2014. Pharmaceutical company, they've got a crazy instrument that likes to put 30,000 tiny files in a small directory. From a size perspective, the experiment is trivial. It's like 5 or 6 gigs of data. However, copying that 5 or 6 gigs off of the instrument to the sort of network-attached SAN environment took more than an hour. And it was incredibly disruptive to the operations of the pharmaceutical company. And the reason why is that the SAN vendor, the SAN technology that they were running, wasn't really well built to handle small file metadata. So the idea of a small directory with 30,000 tiny files was just bringing the storage system to its knees. So the problem is that there are a ton of big, expensive, gigantic storage systems that handle small file ingest fine. Actually, the easiest one is you go to one of the all-flash vendors and you buy a giant flash array. The problem is that the use case for this particular company, because their experiments were so small, we needed a usable system in the 4 to 8 terabyte usable range that could handle small file ingest. That was incredibly difficult to find a low end, not a low end, but a smaller scale usable storage system that excelled at this particular use case. I have to call out the winner here was actually Nexan, their NST series stuff. Nexan's been kind of a favorite vendor of mine for a long time because they're a really good example. So if you look at inexpensive storage, there's a lot of crap material on the market where they've made really bad engineering trade-offs to get the cost down. Nexan is one of the companies that traditionally has gotten the balance right. They do inexpensive storage, but they do inexpensive storage in a way where the trade-offs are handled well. The other reason why I want to give props to Nexan is that they were incredibly enthusiastic about this use case. Without even my prompting, they went out and they built a test environment, and then they thought I wasn't going to believe them, so they videotaped themselves ingesting my scientific data, and they sent me the videotape. So props to Nexan for actually building a compelling sort of small-scale ingest operation. The second thing is, I don't know if you might have seen these pictures from my talks or from my website. So a nice little picture there, picture there, picture there. This was a 2011 project that we did. We were trying to go very, very inexpensive. So in 2011, we were able to build 135 terabytes of raw storage for about $12,000. That article, the stuff I wrote about that, continues to be the most popular BioTeam blog post ever published. It gets traffic every minute at this point. So the interesting thing here is the next generation is here. The next generation here is with a lot better engineering trade-offs. You've got better redundancy. You don't have to build custom wiring harnesses anymore. And also, this new enclosure supports 6 terabyte drives rather than the 1 or 2 terabyte drives. So another thought exercise for you is, what could you do with 45 6 terabyte drives at a rock bottom price? There's a lot of interesting use cases, possibly use cases that you've abandoned because your enterprise storage was so expensive. There's some interesting things happening at this space. So I'll do some pictures here, but the other thing that's interesting, and I'll talk about this here, is that this chassis that's on my desktop right now, this actually isn't 45 drives, it's 30 drives. The reason why it's 30 drives is they've completely re-engineered the hardware so that this chassis is whisper silent. I wanted to have a video of myself, so you can hear that the fact that this thing is rocking 30 drives and not making any noise. This was developed for the video surveillance industry, where the security people wanted the security videos in their office. They didn't want it in the data center. But I latched onto this because there's a compelling need for big storage in a super silent form factor. There's a lot of us who are operating as islands without dedicated data centers or dedicated IT, and the ability to put 30 drives, whisper quiet into a wet lab or in my office or next to my desk. So if you keep an eye on bioteam.net or ping me in a couple of months, I'm hoping to be blogging about what's going on with this. And in the same way I did in 2011, where we published the sort of real world costs of buying and setting this up, I'll have some real world numbers on Backblaze 2.0 coming up this summer. So the final storage-related war story is from a lab that has a long history of doing really innovative stuff at really low cost. It's the Pineda lab at Johns Hopkins University, and these guys are operating at the petascale at very, very low cost. The particular solution I want to talk about involves the Intel version of Lustre running on top of Linux, running on top of ZFS pools, using commodity servers and the Western Digital RAID hard drives that spin at 5,400 RPM. This is the take-home slide. 2 petabytes raw, 1.4 petabyte usable for $165,000. It's so efficient with a PUE of 1.5 that they're saving more than $10,000 a year on electricity costs alone relative to their other storage. And there's a lot of storage vendors in the sort of trade show floor. Another exercise for you is maybe go talk to storage vendors and how much they would charge you for 2 petabytes raw and compare it against this number. There's very, very interesting stuff happening at the low end, and it's inexpensive enough to potentially be quite disruptive. There's huge caveats, huge use cases. You have to be careful. You have to design for the use case and so on and so forth. But I just wanted to show those last couple of stories as an example of where the interesting bits are happening at sort of the small scale, and also with this story, really up at the high end as well. So now I'm transitioning. I'm going to talk about basically what keeps me up at night. And all of this stuff is brand new, so bear with me as I get through it. So I really want to end this talk with what I think my hardest problems are going to be for 2015 and 2016. So by way of introduction, the first tipping point is that the effort or the operational effort required to acquire vast amounts of scientific data is now far less than the real world cost of storing and managing that data through its full life cycle. There's petabytes of open access data available for download on the internet. It is trivial for a single scientist to generate tens and tens and tens of terabytes of data with laboratory instruments that are just getting cheaper and cheaper and cheaper every year. So we have a real problem. The cost of acquiring data is way lower than the cost of storing data. So we've got a huge problem there. The second issue is that if you talk to scientists, they're still in the mind storage is cheap and near infinite. They're influenced by the fact that a terabyte drive costs $40 at Costco these days, and it's difficult to have those conversations with them. Previously, we've had a lot of things where we're doing data triage. We delete primary data because we can go back to the -40 freezer and repeat the experiment. I don't think that's sufficient moving forward. We're actually at a time where sort of the free storage ride is over, and you can expect in the future now that I think scientists are going to have to articulate a scientific or business requirement for a large storage request. The answer is because I need it is I think not going to be sufficient, looking at some of the costs and engineering involved in supporting it. So the third tipping point is that I've spent a lot of time and a lot of years building centralized infrastructure. You put the data in one place, you glom the computer on top of the data, you bring the users to the converged environment over a VDI or remote desktop or SSH. That works. The problem is that data spread is unavoidable. And even if I take an operational or corporate stance that everything science, everything scientific computing is one data center, one centralized facility, that's not going to work. Terabyte scale laboratory instruments are popping up everywhere. They're going to be in the Walmart the Walmart point of care clinic. They're going to be at your satellite field office. No matter how hard you stamp your feet and shout, petascale or terabyte scale data spread is going to happen. It's going to happen no matter what. We can't stop it. It's basically an unavoidable trend at this point. So the problem here is that I've got this center of gravity problem. Back in the day, I used to be able to put all my stuff in one data center and bring the users in over a remote desktop. That's not going to be a tenable or viable approach. 2015, 2016, moving on. So I've already talked over the slide, and one of the biggest drivers is these terabyte scale instruments that are cheap, they're pervasive, they're showing up everywhere. And it's not just genome sequencers. That's the cliche that we all use. It's mass spec machines, it's confocal microscopes, it's 3D ultrasound machines. It's just about any laboratory instrument you can imagine these days. The other issue, I've already talked about this, is that the future of data-intensive analytics is involving multi-site, multi-partner, environment collaboration. We have an unavoidable spread now if we're looking at a collaboration or partnership-centric future. The other issue here is, like I said, there's basically petabytes of free data, sitting on the internet if you wanted to download it and make use of it. So the sort of issue here is that now switching back to erasure coding and the technical bits between object storage, you don't get the greatest benefits of object store until you light up site location number 3, or in some cases, site location number 4 and site location 5. So if you're buying all into object store, there are some capabilities that you gain when you expand your footprint beyond one data center and you go to site 3, site 4, and site 5. So basically what I'm trying to summarize is that as hard as we've tried and as successful as we've been in the past with a centralized scientific computing environment, that does not hold. It's not going to hold for the future. We cannot stop the spread of sort of terabyte scale data producers and terabyte scale data consumers. So you've got basically two viable options moving forward. You can continue on with your sort of centralized everything stack, but you have to buy into the fact that you're going to rapidly have to increase the speed and capability of your connections to the outside world, and probably speed and capability of your connections to other buildings and other labs. The second option is you can go with the flow and you can sort of recognize this sort of cloudy and distributed future. But the fact of the matter remains, what you have to do to go with the flow is the exact same thing. You've got to invest in bigger, better, faster, wider connections to the outside world, wider connections to the world. So I'm leading up to something with this. It all boils down to, for me, terabyte scale data movement is the grand challenge for our world for the next couple of years. And it's actually going to be far harder to solve than the data tsunami sort of transition from terabytes to petabytes that we went through a couple of years ago. It's nasty, and it's going to be a difficult couple of years. And I'm going to try to scare you with the next bunch of slides. So history time. Historically, from a research computing perspective, it's been relatively easy to play nicely with the enterprise. I have a long history of going out and taking rogue IT operations set up by R&D and sort of retrofitting them to fit the enterprise global standards and making sure that the scientists are working in harmony using, enterprise standard vendors, building block storage, everything else. We've got a 20-year track record of research IT working with enterprise IT to make our infrastructure stuff play nicely. So it was relatively easy to align our needs with the need of the business. When it comes to networking and data movement, it's not as clear anymore. So the problem here is that got to prepare for pain. This is really where I'm going here. The large-scale data movement is going to be a nasty hassle for us, and I'm going to go through a couple of issues. So number one, the current state of hardware, the current state of our LAN and WAN stacks are really, really bad for our use case. All of the existing networking technology that's in use in the organizations that we work for has been built to support hundreds, thousands, or tens of thousands of little tiny flows, people web surfing, using voice over IP, using WebEx. They're purpose-built for tens of thousands of tiny flows. They are not purpose-built for what people call the elephant flow, the 1 10 gig data movement of trying to move a terabyte file across the network from one place to another. The second issue is the ratio of our connections, internal to external, are way out of whack. If you buy into what I'm saying, a 1 gig connection to the internet's probably not enough. Above a certain scale, you're going to be looking at more than a gig and possibly 10 gig connections to the outside world. You talk to enterprise people about their long-term networking roadmaps, 1 gig internet connection isn't even on the roadmap. And if you tried to suggest to them you needed a 10 gig pipe to the internet, they'd throw you out of the room. So we've got this issue where there's some education that we need to get across. Issue number 3 is, if you buy into the fact that I'm saying data spread is unavoidable, it's not just bandwidth at the core that matters. It's bandwidth to other buildings, other labs. It's bandwidth to top of rack. It's bandwidth to the outside world. The problem is that if you go in to talk to enterprise networking folks, a lot of them are really smug about the fact that they can do 10 gig Ethernet, or they'll brag a little bit about how their core switch can do 40 gig. So, BioTeam people, we walk in there and, we say, hey, what's your plan for 100 gig, or how do you like the new Juniper stuff? And jaws just drop. They have no expertise, no experience, no budget, and no long-term planning. If you're lucky, an enterprise might have 40 gig today, and 40 gig is part of their roadmap. Too many of them today are freaking smug about 10 gig, and that's just not going to fly moving forward. The second thing is that I've screwed up a lot. I've blown up HPC environments. I've blown up storage arrays. Historically, the blast radius from a nerd like me screwing something up was relatively small. I would disrupt and annoy the scientists. If I was really, really bad, I might delete some data. The problem here is that we have an incredibly dangerous scenario where the blast radius for something going wrong is going to affect the entire company. You can take you can knock the entire company off the internet. You can take down Link or the voice over IP, or your bandwidth is so high that all the security cameras stop sending data over the internet. So the problem here is that prior to networks becoming involved, the blast radius from a scientific screw-up was much smaller and much easier to deal with. Now we're dealing with networks that touch everything everywhere, and the risk is much, much, much higher for what we need to do moving forward. So summarizing what we need ludicrous bandwidth at the core. We probably need something on the order of 10 to 40 gigs going to top of rack edge between buildings. We need to really sort of look at our long-term planning for internet connectivity and figure out if it's aligned with the types of data that we need to move. And most importantly, and probably hardest, we need networking infrastructure that can handle the elephant flows rather than the mosquito flows of the sort of tens of, hundreds of people sort of surfing the web at the same time. The problem is that this is going to be very, very difficult to put into practice in the real world. Issue number 4 here is that I have 20 years of history and trust and relationships with enterprise IT and enterprise operations people. They know me. They know I can represent the needs of the scientists. They know I'm not going to screw up their world. The problem is that we don't have that level of trust and relationship with the people who typically do WAN or MPLS or external connectivity, let alone firewall and security ops. So we're starting from scratch here and having to build relationships. And many times the firewall people or the WAN people have never even met the scientific IT people. So we're starting these conversations, ground zero. When it comes to the data center and storage teams, I have 20 years of history and trust built up. The next issue is that one of the really great things about research IT is that we have an incredibly good bench of talent. We have people who are, might be better at storage and networks and servers than some of the enterprise IT people. We don't necessarily have that bench when it comes into the weird stuff you have to be expert at this scale. We don't have good shadow IT skills with ASN prefix filtering, BGPs, routing, firewalls, dark fibers. We either have to build up that experience internally, which is going to be really hard, or we need to very, very quickly build that bridge of trust with the enterprise networking folks. So issue number 6, cost, cost, cost. Have you seen what Cisco charges for a 100 gig line card these days? You'll be shocked, I'll tell you. The other issue is Cisco. Cisco's kind of the elephant in the room. I'll be blunt and I'll be candid. Cisco is not the first choice in greenfield environments for building out this type of infrastructure. The problem is that we have companies with multi-decade, hundreds of millions of dollars in investments in Cisco infrastructure. But more important than the investment is they have a deep staff of people who know Cisco. They can manage it, they can control it, they can administer it. So we're going to have a very difficult conversation where, does it make sense to continue on in the Cisco world, bring in new hardware, new technologies, but kind of keep the install base? Or is this one of these special purpose things where maybe it makes sense to consider other vendors, other products, and other technologies? It's easy for me to say as an outsider, and it's easy for me to say on a greenfield project just buy, brand X, vendor Y. The real issue is going to be balancing the operational and financial cost of staying on the incumbent vendor versus what are the risks and benefits for possibly looking at alternatives. The 5th issue here is, firewall, SecOps, and incumbent vendors. I've got a story. We had a 10 gig connection to the outside world for a pharmaceutical company. Pharmaceutical company wants to run their security controls, so we bought a firewall that was capable of 10 gig. We were running without the firewall at 9.5 gigabits a second. As soon as we turned on the firewall, the data flow dropped to below 1 gig. There is a really beautiful answer, or a really beautiful outcome to this story. We got the firewall working. We got the firewall passing data at 9.5 gigabits a second with the full pharmaceutical company security controls on it. However, the cost was very high. We monopolized the best of their global network engineers, the best of their firewall people, outside firewall experts, and the research lab from the firewall company. We monopolized those people for months in order to get this thing working. So the really awesome story is we got a corporate firewall to work at 10 gig speed. All the pharmaceutical security controls are in place. From an operational perspective, the cost was high. We tied up some of the best people in the company for months to get this done. That might not be scalable. That might not be portable, sort of moving forward. So sort of wrapping up, actually, I might be doing OK on time here. Petascale's the norm, not the exception. For me, compute power is kind of a commodity, except at 60,000 cores, where it's still hairy and interesting. We're coming to a transition point where historically it's been relatively easy to align the needs of research computing with enterprise computing. I don't think that's going to be the case these days, particularly when it comes to networking and network-based data movement. But we've also got to come to grips in our 5- and 7-year technology planning that the days of single data center hosting R&D are probably over. It's not our fault. It's because of these terabyte scale inexpensive instruments just literally popping up everywhere. So to solve this, we're going to need a massive increase in connectivity to the outside world. We need networks, switches, routers, and firewalls that can handle this sort of elephant-based data flows. A very, very serious case where our enterprise networking stack is not really aligned with what we need to do now moving forward. And at the same time, we have to balance this against all of the standard capability, cost, performance, and security requirements. So there's no easy path forward. We actually need new hardware, new reference architectures, and new best practices. Probably the meat of the next couple of BioTeam talks over the next couple of years is going to be concentrating a lot on these areas. So this brings us to the final bit, which is if you haven't heard this buzzword before, be prepared to be sick of it. It's gonna in the same way that big data and cloud took over your world, Science DMZ is going to do the same thing. The fact of the matter is that there is only one viable reference architecture that BioTeam has seen that can solve these problems. It's in use today. It's not BS. It's real. It's pioneered by the people in the high energy physics community who, to us, we're babies. I mean, the high energy physics, they've got petabytes per second of data production. So the issue here is that there is a proven concept. It came out of the high energy physics world. It's called Science DMZ. And it's probably the only viable method that BioTeam has seen. And if you look at it, I can tell you in all honesty, we have 3 Science DMZ projects going on right now, 2014, ranging at speeds from 10 gig to 100 gig. It's probably the beginning of a transition for a lot of people in a lot of organizations. And just by way of announcement, probably sometime this fall, we've glommed onto the sciencedmz.org domain name. And in the same way that I took over gridengine.org and tried to push sort of, non-markety, useful information out to the community, we're going to try to do the same thing with sciencedmz.org. So I might actually have time to explain this graph. This is the come to Jesus graph that converts non-believers to believers. This graph here is the top line is showing a data flow without packet loss. The second lines are showing what happens to the speed of your data flow with the same amount of packet loss, but at increasing distance. And without talking over this slide, what I'll show you here is that this is a situation with 0.0046 packet loss. If you talk to a network engineer, they'll probably say, what are you complaining about? That's normal. That's how our network behaves. If you even had 1% packet loss, I've run into network engineers who don't think that's a big deal. This is the catastrophic behavior of fractional packet loss. As soon as you get beyond your building, you're probably, at 10 milliseconds here, you're probably talking about metro scale networking distance. If you want to move data beyond the city that you're operating in, with 0.0046 packet loss, you've gone from 10 gigs down to 1 gig throughput. So one of the interesting things about Science DMZ is that it's not actually all about speed. It's not actually all about security. The #1 design goal with Science DMZ is we need to construct networks that behave appropriately, meaning that they don't drop packets, because the drop packet, even at a fractional scale, is absolutely catastrophic to large-scale scientific data movement, beyond the sort of 10 millisecond round-trip time. So I'll end this talk with a couple of final announcements. The people behind Science DMZ, ESNet, they do fantastic free educations and training webinars. The problem is that they typically offer those webinars to groups that need custom content and custom materials, in particular regional members of Internet 2 and things like that. So what we got the Science DMZ people to do is we're going to do a 2-hour webinar on May 18th, no marketing, we're not going to sell you anything. It's going to be 60 minutes of the ESNet people talking Science DMZ and 60 minutes of them hanging around asking questions as well. And the reason why we wanted to do this is that we wanted to do a Science DMZ intro without the sort of regional Internet 2 or sort of other content. We wanted to make it strictly for life science. So we're limited to 100 seats because that's all I can afford on the WebEx product. But if it sells out, we'll do more of them. The second thing that I can't believe I even get to announce this because I love toys, I love infrastructure. BioTeam is going to be opening up a 100 gigabit converged infrastructure lab. It's going to be hosted at TAC, the Texas Advanced Supercomputing site. We've got vendors donating storage, networking, security kit. TAC is going to let us access their 100 gig pipe to the internet. They're going to give us whatever shares we want on their supercomputers. And the goal here is that BioTeam and others want to prove, test, and validate the reference architectures for Science DMZ. And we're going to do this in an open lab that anybody can come and play with. And I'll tell you that the goal #2 is also there as well, is that our goal is to have a really killer demo for Supercomputing 2016, which happens to be in Austin, Texas. So the stars are aligning for doing really interesting things in a converged IT lab that happens to sit in Texas. So I'd say stay tuned for this. This is still very much in the works, but we really do hope to open a collaborative, come in, let us sort of show you this stuff, or possibly let you build your own architectures and sort of kick the tires in a real world environment. So I'm incredibly psyched to be able to sort of mention this here today. So that's it. The final thing, that was 144 slides in 50 minutes, and there is one last thing. So I couldn't do this talk this year, this week, without mentioning the fact that the only reason I'm here to sort of give this talk is because 100 years ago, Turkey failed to exterminate me and my family. So this is the 100-year anniversary of the Armenian genocide. It's particularly notable because April 24th is when sort of Armenians gather together to sort of remember and agitate against the denial that's going on here. So sorry to bring politics in here, but I couldn't do it this year, this week, without mentioning the fact that there's really only one reason I'm here and sort of able to give you, hopefully, useful and sensible info. So thank you very much. We actually have time. I ended 10 minutes before, and that was 145 slides now. Thank you very much.